So our first question is evaporation or loss from oxygen tank. Liquefied gases are sometimes stored in well insulated spherical containers vented to atmosphere. Develop the expression for steady state heat transfers through walls of such container with radius of inner and outer walls being R0 and R1 respectively, and the temperature at inner and outer walls T0 and T1. The thermal conductivity of insulation varies linearly from K0 at T0 and K1 at T1. So the solution for this A part is, now let me define all the variables we will use in this problem. R is the radial coordinate measured from the center of the sphere in units of length. Here we use centimeter. R0 is the inner radius of insulating shell, that is the radius of inner wall of the container. R1 is the outer radius of insulating shell, the radius at outer surface. T0 is the temperature at the inner wall of insulation, which equals the boiling point of liquid oxygen, which is minus 183 degrees Celsius. T1 is the temperature at outer wall of the insulation, which is 0 degrees Celsius, the ambient temperature. In this question, we need more variables like QR, Q0 and capital theta, where QR is the heat flux in the radial direction, meaning the rate of heat transfer per unit area in the R direction in units of calories per second per square centimeter. Q0. Q0 is the total heat flow rate, means the total energy per unit time flowing inward through the spherical shell in calories per second. Okay, and the capital theta, it's a dimensionless temperature. We are about to define it. It is dimensionless number between 0 to 1. Now, because K varies with temperature, so the K varies with temperature, therefore K minus K0 all divided by K1 minus K0, which is equals to T minus T0 and T1 minus T0. Both are in divisions, which is equals to capital theta, which is a dimensionless temperature. So we have get capital theta here. So we have to simplify this question. So we have some key steps here. First, K varies linearly. Define theta, capital theta. T minus T0 divided by T1 minus T0. Energy balance on thin shell. D by dr R square QR is equal to 0. Applying Fourier's law, which gives d by dr R square K d theta d by dr, which is equal to 0. We now integrate once with respect to R to get R square K d theta by dr, which is equal to C1, or we can say K d theta by dr is equal to C1 by R square. So let's understand why we integrate here. Inserting the expression for thermal conductivity as function of temperature and integrating again, we find K0 theta plus half K1 minus K0 into theta square is equals to minus C1 by R plus C2. Now we apply boundary conditions. The boundary conditions at R0 0 is equals to minus C1 by R0 plus C2, and at R1 1 by 2 K1 plus K2 plus K1 plus K0 is equals to C1 by R1 plus C2. subtracting the first equation from the second, eliminate C2, where we don't need C2 here, and gives equation for C1. So we get half of K1 plus K0 is equals to C1 into 1 by R0 minus 1 by R1, which is equals to half of K1 plus K0 R0 into R1 divided by R1 minus R0. The heat flow inward through spherical shell at R0 is now Q0 is equals to 4 pi R0. This will be positive now, that thermal conductivity, dt by dr at R is equals to R0, and which is equals to 4 pi R0 square is again positive, okay, T1 minus T0 d theta by dr at R is equals to 0. The derivative of dimensionless temperature can be found. This is our equation. Evaluating this expression at R is equals to R0 gives K0 d theta by dr at R is equals to 0. So half of K1 plus K0 R divided by R1 minus R0 multiplied by R0. Putting this expression into formula for Q0 gives this equation. So this is our answer of first part. Clear this. So for second part, since the most of the quantities are given in CGS system, we will be converted all quantities into that system. The quantity Q0 may be evaluated thus: Q0 is equals to 4 pi into 36 into 2.454 into 48 into 2.54, and these terms. So we finally get our Q0. The factor 4.136 into 10 to the power of 3 needed for converting units of thermal conductivity is obtained from the table F3.5, which is very important. The rate evaporation of oxygen is then here we have to find rate. Our rate is equals to 2.8182 divided by 11636 multiplied by 3600, which is ultimately 6.201 gram per ml per hour, or R is equals to 6.201 multiplied by 32 divided by 100 is equals to 0.198 kg per hour.